Hi everybody. In the last video we reviewed the inverse trigonometric functions, and so now we're going to take a look at the derivatives of the inverse trigonometric functions. And as we'll soon see, there are a lot of applications for the inverse trigonometric functions as well as their derivatives, which are oftentimes used to measure the rate of change of objects. So down here we have a theorem detailing the derivatives of all of the inverse trigonometric functions. For example, the derivative of the arc sine is 1 over square root 1 minus x squared, and correspondingly derivative of the arc cosine is negative 1 over root 1 minus x squared. You have the derivative of the arc secant here, 1 over absolute value x, take note of that absolute value, times the square root of x squared minus 1, and derivative of the arc cosecant is negative the derivative of the arc secant. Derivative of the arc tangent is 1 over 1 plus x squared, and correspondingly derivative of the arc cotangent is negative the derivative of the arc tangent. Now let's take a look at a proof of a few of these. We're just going to look at the proof of number 5 here and leave the other two right here for you to take a look at. Now once you have 1, 3, and 5 proven, well, you can see that 2, 4, and 6 would be very similar to the proofs of 1, 3, and 5. So let's take a look at the proof of number 5 here. So we want to prove that the derivative of the arctangent is 1 over 1 plus x squared. Notice I used this slightly different notation. You'll see why in a second. So if we start out with this function, we want to take its derivative. So before we do that, let's actually take the tangent of both sides. And this is what we get. Now the right-hand side here, tangent of the arctangent or inverse tangent of x, that's just going to be x. That's very reminiscent to f of f inverse of x equaling x. Recall that this is the relationship that a function and its inverse has. So you see we have the tangent is playing the role of the f, we have the inverse tangent function right here, and so this is exactly what we have up here, just with the word tangent in place of the word f, in place of the letter f. Now keep in mind the tangent to the negative 1 power notation here. In this case that does not mean 1 over tangent, that means the arctangent or the inverse tangent function. So now what we have is now I just used the notation y of x to indicate that this y right here is a function of x. See, it's this function of x right here. And now let's differentiate both sides with respect to x. So we'll just take the derivative of both sides. Now this side right here is easy. That's 1, of course. Now this piece right here, you have to do a little chain rule. So this is going to be okay, right, so here we just did the chain rule. Notice the dy's cancel here. We can think of them as canceling, and they give us back the d dx right here. Now this piece right here, derivative of tangent is secant squared. So that's going to be, now let's divide the secant squared to the other side, and we get there we go. Now, we still need to put this back in terms of x's, right? We want to get to this point right here. We're not there yet. We're almost there. So now what we're going to do is we're going to use a trig identity. Recall this trig identity. Okay, so there is a trig identity. That actually comes from this trig identity. You should recall this famous trig identity. That's our Pythagorean trig identity. Sine squared plus cosine squared is 1. And the way you get this identity from this one is by just dividing everything here by cosine squared. Divide everything by cosine squared x. So cosine squared divided by cosine squared will become 1. Sine squared over cosine squared will become tangent squared. And 1 over cosine squared becomes secant squared. So that's how you get this identity. And now let's just replace the 1 plus tangent squared y right here. Let's put that in place of the secant squared y. And we get that y prime. But up here, recall that tangent y is equal to x. And so just put x back in place for the tangent y right here, and we get our result. So there you go. dy dx for this y is 1 over 1 plus x squared. And that's exactly what we wanted to prove right here. And the other ones are proven similarly. For number 1 right here, you would use this identity right here. Now let's take a look at a few examples. So let's just evaluate the derivative of these two functions right here. So we want to take the derivative of the arc sine of 3x. Now recall that So let's evaluate the derivative of these two functions. First of all, the arc sine of 3x, and then the arc secant of x squared plus 1. And don't get confused, I use the notation sine to the negative 1 power to indicate the inverse sine function here. So we want to differentiate this. Well, notice that the x right here and the 3x right in here, they don't match, so that means we're going to have to use the chain rule. Right? If you recall the formula, I have the formula copied right here. Derivative of the arc sine is 1 over square root 1 minus x squared, but you see the x here and the x that you're differentiating with respect to must match. What's inside the parentheses here? They must match. They don't in this case, so we have to use the chain rule. So we will let the 3x be a u, and so this is going to be d du, arc sine of u times du dx. And this term right here is going to be and derivative of u with respect to x is just going to be 3. And then substituting what u is back in here, u is 3x, so putting a 3x right in here, we get our answer. And there we go. So that's our derivative of the arc sine of 3x. Let's take a look at this one. So we want to evaluate well, notice once again that the x here and what's inside the parentheses here don't match, as they do in the formula down here, you see. They match. So we're going to have to use the chain rule again. So we're going to have to let this be a u. So u is going to equal x squared plus 1. And so this will equal now this piece right here, you see the u's do match. The u right here and the u that we're differentiating with respect to, they both match. And so we can use this formula right here. And so this will equal 1 over Now the derivative of u is x squared plus 1, so this is going to be 2x. And then substituting what u is in for these two u's down here, we get our answer. And you could simplify this a little bit. Notice x squared plus 1 is always positive, so actually we don't need the absolute values here, although there's nothing wrong with leaving them in. And then foiling out x squared plus 1, that is x to the 4th plus 2x squared plus 1, and then this minus 1, so those 1's will cancel. And then so we're going to have down here and we have our answer. Just notice once again that I took away the absolute values because x squared plus 1 is always a positive number, but I could have left them there. There's nothing wrong with that. Now let's take a look at this application problem down here. So here we have an object that's dropped from a height of 500 feet, and a camera on the ground 1,000 feet from the impact point records its fall. Find the rate of change of the angle of elevation of the camera at the time of impact. Alright, so the first thing you want to do for word problems, if possible, draw a picture. So here's our picture for this problem. So we have an object up here, it's being dropped downward. Now its initial height is 500 feet. It is falling, so I'm going to denote its distance as s of t. Over here we have the camera, and the angle of elevation is given by this angle right here, and we'll call that theta. And that theta is also a function of time t. And we're also told that this distance here is 1,000. So we want to find d theta dt when the object hits the ground, and it hits the ground when its position function is 0. Now what we want to do is find theta as a function of time t. And then we'll find how long it takes for the object to hit the ground. Then we can take the derivative of theta of t and then plug the number in representing how long it takes for the object to hit the ground into theta prime, and we'll get our answer. Now from this picture here, let's notice that we can write the tangent of theta of t. Notice that that is going to be equal to that. Now let's see if we can find s as a function of time t. You see, because now from here then we get that theta equals the arctangent so it's the arctangent of s over 1,000. So now we need to try to find s as a function of t, and then we can plug that in here. Then we'll have theta as a function of t, and we'll be able to differentiate this. Now recall from Calculus 1, the position function for an object thrown upward or downward near the surface of the Earth is given by this. Let me put it right up here. So recall that this is a position function for an object thrown upward or downward near the surface of the Earth with an initial velocity v0 and an initial height of s0. Now this is in the English system. If this were in the metric system, that 16 would be 4.9. That would be in the metric system. So the units here are feet. Those are the units for s of t here. Now in this case, we're told that the object is dropped from an initial height of 500 feet. So for our problem right here, the v0 is 0, and the S0, that's the initial height, that's going to be 500. So therefore, S of t there we go. So now we can plug that in for the S right here, and we'll be able to differentiate this. Now let's find how long it takes to hit the ground. We need to know that. Well, if we set this equal to 0, now solving this for t, then we'll get that t equals square root of 500 over 16, right? Just take the negative 16t squared over to this side, divide the 16 under the 500, and then you have to take the square root to get rid of the square there. Now we should have a plus or minus here, but we're not going to put the minus because we're going forward in time. We're not going backward in time. So we use a plus here. Now let's also note that let's put this in for our S right here, and we get and now we need to differentiate this with respect to t and put this number right here in place of the t after we differentiate. So let's do that up here. Now we're going to have to use the chain rule here, so we're going to have to let this be a u. So that's going to be u. So the derivative of the arctan with respect to u first is going to be 1 over 1 plus u squared. So we're going to get, now u squared, remember that's the so there's the derivative of the arctan of u with respect to u. 1 over 1 plus u squared. Now I need to multiply by du dt. So when I differentiate negative 16t squared plus 500 over 1,000 with respect to t, this is what I'm going to get. Now just note that I can write that like this. So when I differentiate this piece, that's going to go to 0. And the derivative of this piece is going to be negative 32t over 1,000. And there we go. So there is theta prime of t right here. Now what we need to do is put this number right here in place of all the t's here, right here, and right here, and then just calculate that number out. So then theta prime of, and let's see, square root of 500 over 16, that will simplify as 5 times root 5 over 2. So this quantity right here is the square root of 500 over 16 simplified. And now plugging this in for the t here and here, I'm not going to write all that out, but you can do that on your calculator, and you'll get negative 0.1789. Let's just round that to 4 decimal places. So that's our answer, and the units there would be radians per second. And so that is our final answer. So that is how fast the angle of the camera is moving when the object hits the ground. And notice that this negative makes sense. That makes sense because this would be a decreasing angle. As the object is dropping, the angle is decreasing, so it makes sense that we should have a negative there. And that concludes our discussion about the derivatives of the inverse trig functions with some examples.